Beyond limits. The future of science, space, and human evolution. What if everything we thought we knew about reality was just the surface of something far deeper, something beyond space, time, and even matter itself? What if gravity isn't a force but an emergent illusion of an underlying computational structure? What if black holes aren't cosmic dead ends, but vast information processors storing the secrets of the universe? And what if we've been looking at energy all wrong, overlooking the key to extracting unlimited power from the very fabric of space-time? In this video, we're tearing apart the limits of human knowledge and stepping into the future of physics, energy, and space travel. We'll explore radical new theories that could redefine science itself: zero-point energy extraction, black hole information paradoxes, emergent space-time, and the potential engineering of gravity itself. This is not science fiction. This is the cutting edge of theoretical physics, where speculation meets science, and where humanity's next great breakthroughs may be waiting. Buckle up, because once you understand what we're about to uncover, you'll never look at reality the same way again. Let's begin. Quantum gravity and unified physics. A deeper approach beyond conventional thought. The challenge of merging realities. Physics today is an uneasy truce between two seemingly irreconcilable frameworks: quantum mechanics and general relativity. The former governs the minute, probabilistic realm of subatomic interactions, while the latter describes a vast, smoothly curving cosmic landscape where gravity is not a force but a manifestation of warped space-time. The problem is that these two paradigms clash in the most extreme environments: black holes, the early universe, and potentially even the quantum fabric of reality itself. At present, every attempt to merge these models has met resistance. String theory attempts to unify forces by proposing tiny vibrating loops existing in higher dimensions, yet lacks empirical confirmation. Loop quantum gravity proposes a fundamentally discrete structure of space-time, yet remains incomplete. Every path seems to lead to paradoxes, endless infinities in calculations, contradictions in assumptions, and a sheer lack of experimental feasibility. The most frustrating aspect? Our very means of observation, tied to classical measurement and macroscopic instrumentation, may itself be an obstacle to revealing quantum gravitational effects. But what if we are searching for answers in the wrong framework? What if space and time are not fundamental at all, but emergent properties of deeper, more abstract structures? The prevailing assumption in physics is that we should unify gravity by making it quantum. However, the solution may instead require us to dequantize our understanding of matter. A different perspective: the information paradigm. One of the most promising deviations from conventional theory is the idea that space-time itself is a computational structure, akin to a processing network rather than a continuous fabric. This aligns with the emerging concept of holographic reality, which suggests that the three-dimensional universe we experience may be a projection of fundamental quantum information encoded on a lower dimensional boundary. If this is true, then gravity, rather than being a classical force, might emerge as a secondary effect of entanglement and information flow across this network. Instead of seeking to quantize space-time, we should be exploring how gravity emerges from the complex interplay of informational relationships, the computational structure underlying reality itself. Furthermore, if gravity is a byproduct of deeper, non-spatial data structures, then our current difficulty in detecting gravitons, hypothetical quantum particles of gravity, may be due to the simple fact that they do not exist in the way we expect them to. Being that of discrete particles, gravity may manifest from large-scale coherence effects in an underlying information matrix. New directions for testing unified theories. Since direct experimental tests at the Planck scale, where quantum gravitational effects should manifest, are currently unfeasible, we must explore alternative indirect avenues of validation. Some unconventional but potentially groundbreaking methods include extreme quantum computing and simulation. If space-time is emergent from entanglement, then quantum computers with high-dimensional entanglement capabilities should be able to simulate gravitational behavior at a small scale. Instead of waiting for natural phenomena, we could construct artificial conditions, where gravitational-like effects emerge in synthetic environments. High-energy gravitational wave anomalies. Current gravitational wave observations match predictions from relativity, but what if subtle deviations appear in highly energetic cosmic events? Researchers should look for small distortions in waveforms that could indicate quantum gravitational corrections, especially in black hole mergers. Non-locality tests in gravitational systems. If gravity is a product of entanglement rather than a true force, then large-scale experiments testing whether gravitational fields exhibit non-local quantum correlations could reveal fundamental new insights: thermodynamics and entropy as a probe for space-time structure. If space-time is fundamentally informational, then concepts like entropy and thermodynamics should show deep connections with gravity beyond what we currently understand through black hole physics. Exploring these connections may reveal novel gravitational behaviors at microscopic scales, radical assumptions that could lead to breakthroughs. To escape the current stalemate in quantum gravity research, we must be willing to entertain alternative assumptions that contradict standard models. Here are some possible radical departures. Spacetime is a derived effect of computational processing. If the universe is best described as an evolving computational network, then our perception of continuous space and time is merely an emergent phenomenon from information processing rules. Gravity might then be better understood in terms of network topology rather than field equations. Matter and energy are not fundamental. Only relationships are. If we go deeper than both quantum mechanics and relativity, we may find that particles, forces, and even dimensions are secondary effects of deeper relational data structures. A theory of quantum gravity might be a theory not of things, but of interactions existing in a purely informational framework. The arrow of time emerges from quantum decoherence in spacetime. Time, as we experience it, may not exist at the fundamental level, but instead emerge as a statistical trend from entanglement dynamics. If time is a construct rather than an independent dimension, then quantum gravity theories should abandon fixed timelines in favor of probabilistic, path-dependent structures. Consciousness and gravity may be connected through information processing. While speculative, some researchers have hypothesized that consciousness itself might be entangled with quantum gravitational effects at microscopic scales. If true, then studying the neural synchronization patterns in highly coherent cognitive states could yield unexpected insights into how gravity and information are linked. That completes Chapter 1. Be sure to check out my channel for future chapters. Thanks for watching, everyone.